Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This is a series of videos for Chemical Engineering Thermodynamics 1, and we are looking at Chapter 4, covering entropy, and we will begin doing some simple applications of the second law of thermodynamics in this lesson. So, the second law, in essence, says that delta S for the universe must be positive or equal to zero. Positive indicating a reversible or irreversible process. Equal to zero meaning that it's a reversible process. And negative indicates that it's something that's impossible. So how can we use this to, do something practical? Well, this does a couple of things for us. One is that it allows us to determine whether or not something's possible or not. It is not at all uncommon for people to try to invent something that isn't possible in the first place, and then they wonder why they can't get it to work. We also can use this so that we can find limits on our reality. So perhaps it's a matter of that I know that this works. How far can I push this variable or that variable and still have something that will function? In this example, we have a heat source at 1100 Kelvin and a heat sink at 300 Kelvin. So our high temperature is 1100 Kelvin. It's going to be isothermal. Our low temperature is going to be what we will remove heat from our system to, and that's going to be also isothermal at 300 Kelvin. And we want to find the maximum possible thermal efficiency for a heat engine that operates between these two reservoirs. So the maximum possible thermal efficiency is going to be for that Carnot cycle. That was what Sadi Carnot envisioned. This would be the best possible. And we know that the thermal efficiency based on that is 1 minus TL over, or TC, over TH, our cold temperature over our hot temperature. Now, it is important that when you look at these ratios as being equal to the heat transfer equal to the temperature ratio, this is only for absolute temperature. We also sometimes call it thermodynamic temperature because this only works if temperature absolutely must be positive, right? This is not going to work if we are using a relative scale like Celsius or Rankine or Fahrenheit. So we need to always be doing this for kelvins and rankines. Now, in this case, I was very kind and gave you temperatures that were already in those units, but if they are not, you want to make sure that they are. So 1 minus 300 over 1100 is going to be, 8/11ths, or let's see, that's 72.7, so 0.727, or 72.7% efficient. Now, this is the maximum that could be possible. This does not mean that's the efficiency that you're going to get, but it also means when you hear, like a politician, there was one of those statements in the past couple of years that, the efficiency on car engines is terrible. We need to see what we can do to improve those. Unfortunately, we've got some practical limitations based on the second law of thermodynamics. So I will not ever be able to achieve an efficiency greater than this. And we will see soon that even getting very close to that is not necessarily practical. Next, let's determine the heat input and output for a coal-fired power plant that generates 2,000 megawatts of power by burning coal at 8.1 times 10 to the 5th kilograms per hour. And they note that coal has a heating value of 33,500 kilojoules per kilogram and we want to determine the heat input and output and find the efficiency of this engine. Now, this is in fact a practical problem, right? So for a cycle, we know that we can say that the first law tells us that the sum of all of the heat transfer is the negative of the sum of all of the power produced. In this case, we have the power is, the 2,000 megawatts, okay? And that is negative because it's producing power, all right? We have burning coal at 8.1 times 10 to the 5th kilograms per hour. That is our mass flow rate of our fuel. And we can use that with this heating value So multiplying the flow rate of the heat source, or coal, by the energy value input of, or output, I guess, of that coal when it's burning, 33,500 kilojoules per kilogram, we can get QH, and the units on this are going to be a little bit wonky. Okay, fixing that. 2 times 10 to the 6 kilowatts divided by 7.54 times 10 to the 6 kilowatts. Those cancel, so 2 divided by 7.54. The thermal efficiency is 0.265, or we could say this is 26.5% efficient. But we also wanted the heat input and output. Now this is my heat input, right? QH is the Q input. What about the heat output? So heat out is going to be Q sub L. And I have sorted ways I could do this, but let's use the first law. The sum of the Q's is equal to negative of the work. In this case, they're all rates, so power, okay? So 7.54 times 10 to the 6 kilowatts plus Q sub L is going to equal 2 times 10 to the 6th kilowatts. Q sub L, therefore, is 2 minus 7.54, or negative 5.54 times 10 to the 6th kilowatts. And that is going to be our heat output, excuse me. So the heat that is lost by the system. Okay. So my last thing is that, once again, I have a recommended video that you can watch from PBS Crash Course on why we can't invent a perfect engine. And I think they do a fantastic job of taking these concepts a little bit further. In our next lesson, we will be looking at an entropy balance, or another way of applying the second law of thermodynamics. Thank you very much for your time.